Hello students, today we will discuss about refraction of light. Refraction of light is the phenomena of change in path of light when light travels from one medium to another medium. You have seen that the bottom of a tank or a pond containing water appears to be raised, or when a thick glass slab is placed over some printed matter, the latter appears raised when viewed through the glass slab. Why does it happens? It happens due to the refraction of light because light is traveling from one medium to another. So when light travels from one medium to another, there is change in velocity of light. Or you have observed that a lemon kept in water in glass tumbler appears to be bigger than its actual size when viewed from the sides. Or there is apparent displacement of a pencil partially immersed in water. The light reaching you from the portion of the pencil inside water seems to come from different direction compared to the part above water. This makes the pencil to be displaced at the interface. Similarly, the latter appears to be raised when seen through the glass slab placed over it. All these phenomena occur due to refraction of light. So this shows that light does not travel in the same direction in all medium. It appears that when traveling obliquely from one medium to another, the direction of propagation of light or the direction of traveling of the light in the second medium changes. This phenomena of change in direction of light when travel from one medium to another is called refraction of light. Now refraction through a rectangular glass slab. So to understand the phenomena of refraction of light through a glass slab, there is a activity. Fix a sheet of white paper on the drawing board using a drawing pins. Place rectangular glass slab over the sheet in the middle. Draw outline of the slab with a pencil. Suppose that this is your drawing board. You have to fix a paper sheet with drawing pins, and in the middle of the sheet place a glass slab. Now draw a normal over here and place two pins at some angle with a normal at any point. When you observe these pins from this side, then observe these two pins from this side and place two pins over here. The, these two pins should be in the same line with these two pins. So take four identical pins, fix two pins vertically such that line joining the pin is inclined to the edge AB. If this is edge AB. Then we will fix two pins at E and F point. Through the opposite side, fix two other pins, say G and H. On the other side, as we have fixed two pins, so we will fix two pins at G and H, such that these pins and the images of E and F lie on a straight line, such that these two pins G and H and images of these two pins and seen from this side should be in a straight line. Now we will move these pins, join the position of the tip of the point E and F. Now when you draw a line draw a normal over here, you will see that there is change in path of light, as you can see here. When light travel from air to glass, it will bend toward the normal. This is your normal, and it will bend toward the normal. And at here, when light travel from glass to air, it will bend away from the normal. When this is called incident ray, this is called a refracted ray, and this is called emergent ray. Now if there is no refraction, then light will come along this path, and this, if there is no refraction, this will be parallel to the emergent ray, and the perpendicular distance between emergent ray and the light which is coming along this line when there is no refraction, this perpendicular distance is called lateral displacement. At here, if there is no refraction, the ray will emerge parallel to the emergent ray. So refraction is due to change in speed of light as it enters from one medium to the another. Now there are some laws of refraction of light. Here you can see the incident ray, the angle which the incident ray makes with the normal is called angle of incidence, and the angle which the refracted ray makes with the normal is called angle of refraction. Now there are two laws of refraction of light: the incident ray, refracted ray, and the normal to the interface of two transparent medium at the point of incidence all lie in the same plane. So this is your incident ray, this is your refracted ray, and this is your normal. This is the point of incidence. So at the boundary which separates the two medium is called interface. So at the point of incidence, at the interface, the incident ray, refracted ray, and the normal all lie in the same plane. Next is the ratio of sine of angle of incidence to the sine of angle of refraction is constant for the light of a given color and for given pair of medium. This law is also known as Snell's law. This is true for angle of incidence greater than 0, for angle of incidence greater than 0 and less than 90 degree. If I is the angle of incidence and r is the angle of refraction, then ratio of sine of angle of incidence to the sine of angle of refraction equal to constant. This constant value is called refractive index of second medium with respect to first medium. It is denoted by u, mu, or sometimes by n also. So this is called Snell's law. The ratio of sine of angle of incidence to the sine of angle of refraction is always constant. This constant is called a refractive index. Now what is refractive index? So the ray of light which travels obliquely from transparent medium to another changes its direction in the second medium. The extent of change in the direction that takes place in a given pair of media may be expressed in terms of a refractive index, the constant appearing in the right hand side of this equation. So refractive index is related with the important physical quantity called speed, relative speed of propagation of light in different medium. So light propagate with different speed in different medium. Light travel fast in vacuum with a speed of 3 into 10 to the power 8 meter per second. So the speed of light in air as well as vacuum is in approximately equal, and speed reduces in glass and water. So refractive index depends upon the speed of light in different mediums. Now suppose that light is traveling from medium 1 into medium 2. This is medium 1 and this is medium 2. Let B1 be the speed of light in medium 1 and B2 be the speed of light in medium 2. The refractive index of medium 2 with respect to 1 is given by refractive index of 2 with respect to 1 denoted by n21 is equal to speed of light in medium 1 to the speed of light in medium 2. Similarly, the refractive index of medium 1 with respect to medium 2 is equal to speed of light in medium 2 to the speed of light in medium 1. So if c is the speed of light in air and v the speed of light in medium, then refractive index of the medium is equal to speed of light in air to the speed of light in medium, that is c upon v. The absolute refractive index of the medium is simply called refractive index. So there is a table in which absolute refractive index of some material is given. Air is having refractive index 1.0003, vacuum having refractive index 1. So this is also approximately equal to 1. So in both the cases, air as well as in vacuum, refractive index is taken to be 1. So from this table we can find out the refractive indexes of the different materials. If refractive index is more, the speed of light in that medium is less. If refractive index is less, speed of light in that medium is more. So kerosene having higher refractive index, kerosene 1.44, and water refractive index is 1.33. So kerosene is optically denser than water. Refractive index of water is 1.33. Refractive index of glass is 1.52. Kerosene having higher refractive index is optically denser than water, but the mass density of kerosene is less than the water. So mass density and optical density both are different things.